Have you ever stopped to think about the simple stuff? You know, like on a really hot summer day, how can one thing feel like it's on fire while something right next to it feels perfectly cool? Well, it turns out the answer is hiding in some seriously cool physics. So let's uncover the secret of heat together.
Okay, so picture this. You're at the beach, you get out of the car, and you start doing that crazy high-knees dance across the sand because it literally feels like you're walking on hot coals. But then, you dip your toes in the ocean, and it's just bliss. Refreshingly cool.
But hold on a minute. The sand and the water, they're both getting blasted by the exact same sun, right? They're getting the same amount of energy poured on them. So, why is one painfully hot and the other so nice and cool? That right there, that's the mystery we are going to solve.
Now, to get to the bottom of this, we've got to make sure we're all speaking the same language. We're going to talk about two words that we all use every day, but in physics, they mean totally different things: temperature and heat. So first up is temperature. When we measure something's temperature, what we're really doing is measuring the average energy of its molecules. If those little molecules are just zipping around, vibrating like crazy, well, the temperature's high. If they're kind of sluggish and moving slowly, the temperature's low. It's basically a snapshot of a system's internal energy. Now heat is different. Heat isn't something an object has. Heat is something that moves. It's the name we give to energy when it's being transferred from a hotter thing to a colder thing. So it's not a state, it's a process. It's energy on the move.
And you know what? This single idea explains so much about what we feel. When you touch that hot sand, it feels hot because a ton of heat is flowing really fast into your hand. And when you touch the cool water, it feels cool because heat is flowing out of your hand and into the water. We don't actually feel temperature, we feel the flow of heat.
So, if heat is a form of energy, how do we know for sure? Well, for that, we can thank the absolutely brilliant 19th century physicist James Prescott Joule. He came up with this amazing experiment that proved once and for all the link between mechanical work and heat.
Joule's setup was just so clever. As you can see, he used falling weights to spin these little paddles inside a tank of water. The work being done by those falling weights got transferred to the water by the paddles. And guess what happened? The water's temperature went up. And there was no fire, no stove, no external heat source at all.
This led to an absolutely game-changing conclusion, what we now call the mechanical equivalent of heat. He proved that you could do mechanical work on something and raise its temperature, just like if you'd put it over a flame. Work and heat, they were just two different ways to pump energy into a system.
And he even measured it. He figured out that it takes exactly 4,186 joules of work, that's our standard unit for energy, to get the same result as 1 kilocalorie of heat. And a kilocalorie is just the heat needed to raise 1 kilogram of water by 1 degree Celsius. This number, right here, connects the entire world of motion to the world of heat. It's incredible.
Okay, so we've got that the sun is transferring energy, heat, to both the sand and the water. But that still doesn't tell us why they react so differently. For that, we need to uncover a secret property that's hidden inside every single material.
And this property is called specific heat capacity. We just call it C. Honestly, the easiest way to think about it is as a material's thermal inertia. Or maybe it's thermal stubbornness. A substance with a high specific heat needs a ton of energy to raise its temperature. But one with a low specific heat, it heats up super easily.
Now let's look at the numbers, because they really do tell the whole story. Just look at water. Its specific heat is a massive 4186. Now compare that to concrete or sand, sitting around 840. And iron, it's way down at 452. Water has one of the highest specific heats of any common substance. It is incredibly stubborn about changing its temperature. This chart just makes that difference so obvious. To raise the temperature of 1 kilogram of water by just a single degree, you need almost 10 times more energy than you would need for a kilogram of iron. That difference is just enormous, and it's the absolute key to our whole puzzle. All right, we have all our clues, we know the difference between heat and temperature, and we know about this secret property called specific heat. It is time to put it all together and finally solve the mystery of the beach. This formula right here, even though it looks simple, is the key to everything. Q is the heat energy you're adding, M is the mass of your stuff, C is that super important specific heat value we just talked about, and that little triangle, the Greek letter delta, it just means change in. So delta T is the change in temperature.
So let's use this on the sand. The sun is adding energy, that's Q. Now we know sand has a very low specific heat, a low C.
So because that C value is so small in the equation, even a normal amount of sun energy results in a huge change in temperature, a big delta T. The sand just heats up like crazy. And now, the water. It's getting the same amount of sun energy, the same Q. But water has that massive specific heat value, that huge C. So because C is so big, the exact same amount of energy from the sun results in a teeny tiny, barely noticeable change in temperature, a small delta T. And there you have it. The mystery is solved.
You know, this same principle is the whole idea behind calorimetry. It sounds fancy, but it just means that when you mix hot and cold things together, the heat that the hot thing loses is exactly equal to the heat the cold thing gains. They just trade energy until they find a happy medium. Here's a perfect example. Say you have a hot aluminum pan at 150 degrees and you pour in some cool water that's at 20 degrees. Where's the final temperature end up? It's not halfway. It ends up way down at about 59 degrees. And why? Because the water's super high specific heat lets it soak up a huge amount of heat from the pan without its own temperature shooting up very much.
Look, this isn't just a neat party trick for the beach or something you see in the kitchen. The concept of specific heat capacity, especially water's ridiculously high value, is basically fundamental to how our entire planet works. Our oceans act like a giant thermal battery for the whole planet. They soak up solar energy all day and all summer, and then release it slowly at night and in the winter. That's what regulates our climate. It's why coastal cities have way milder weather than places inland. It's used to cool our car engines, and, in this crazy example, it can even be used to stop truck brakes from overheating when they're coming down a steep mountain. So, when you get right down to it, specific heat isn't just some random number in a textbook. It is a truly fundamental property of matter that shapes everything, from our global weather patterns to the design of the technology we depend on every single day. From the cool ocean breeze to the way you make dinner, this hidden property of matter is working all around you, all the time. So the next time you feel that scorching hot sand under your feet, you'll know exactly what's going on. And you can ask yourself, what else in my world is secretly being run by specific heat?